Good morning, everyone. Thanks. See, I am an engineer, so I would be talking mostly about the real pictures over there. So, please, a disclaimer is that don't assume that I am trying to say that something is not good or you should not be doing a particular process. I would just I would be talking about some negative aspects, but still I work on similar topics. So the point I was trying to make here is that even if there is some question mark on the sustainability aspect of some of the work which I do in my research, we still keep working on that, and we hope that over a period of time will become more sustainable. Okay, and today, since we have because of a lot of effort of Arvind, we have got a Green Valley Hydrogen Valley project in IIT Madras. So I have changed my title a bit. I now say what is the role of green hydrogen in sustainable CCUS. So if you will see whatever I'll talk about. So if you see here, the challenge has been, as an engineer, I always see that we try to propose something. So this is a data which is slightly dated 2018, and at that time it was pretty much expected that we are going to peak around 2020 in the CO2 emission. But obviously we have not been able to do that, and there are a lot of other data in this slide, but since I have lesser time, and now we have a different prediction that we are going to probably peak by 2025. I am not too sure whether 2025 target also we are going to be able to meet. But then there is another data which obviously COP28 going right now, and we have been talking about our CO2 budget. So if you are going to have 1.5 degree rise in temperature, the CO2 budget right now is around 250 billion tons of CO2. And since we emit around 41 billion tons of CO2 every year, which is increasing globally at 1% per year, in India it is increasing at around 7% per year. So if you see this, we basically have a 6 years budget. So within next 6 years, we will be able to cross that barrier of 1.5 degrees, and I really don't see anything is happening in next 6 years actually. If you talk about this 2 degree data, obviously we have around 20-25 years with us, depending upon the rate at which we are consuming. So obviously there is some hope that we will be able to reach this 2 degree target if we start working as of today and we really start implementing some of the technologies which we have. But before we start implementing this technology, I'll take you through some of the challenges which we will have to face as an engineer or as a chemist. If you look into this particular data, you see the power sector. So it basically says that there are 700 billion tons of CO2 which has to be removed by 2050 if we have to meet this 2 degrees target. Now, if you talk about 700 billion tons, so around 300 some tons comes alone from the power sector. And if you see here, the prediction is that the power sector has to go so much renewable by 2050, and that's huge. So much of decarbonization has to happen, not by using fossil fuel, but instead moving from fossil fuel based power generation to renewable based power generation. And then there is CCS, which is obviously we may think that everything can be solved by CCS, but it's only 17% of total abatement which you can do comes from CCS in this optimized scenario, which is again a data from IEA. I am not giving this data from my side. And then you will see energy efficiency plays a significant role in all of these industry, transport, buildings and other transformation. But let me be very frank with you, say for example in transportation, the efficiency has typically not increased of the ICE engine. What has increased that we have better roads, so we are traveling twice as many distance within the same time. So that's how the efficiency has typically increased. But the increase in efficiency we may talk about, but generally does not happen that fast. It's something which has to be. So if you have a take home message here that CCS is going to play a significant role, and then renewable has to be part of the mix. So let's try to understand what renewable, how we in India has been able to do that. So we have been talking about renewable for many years, biomass, and then we say that we are agrarian in this country, we have huge amount of biomass, we should be able to move to renewable, but the data shows that we are not going anywhere. If you look into the data, we were actually using more renewable in 1985 than as of today. It went down and then it is somewhere over here. So still we are hovering around 20%. So this is kind of an organic system. If we are not doing any targeted effort, organically we are not moving towards using renewable. This is very clear. And this is something which we'll have to understand. It's not going to change drastically in next 5 years, 10 years, 15 years, because this is a very long period data. And if we have not been able to achieve this in so many years, and this is not only India specific, I'll tell you, around the world the data is very similar, not very much different from each other. At some point of time, we were producing 90% of our solar panels by renewable energy. Today we are producing 99% of our solar panel by fossil fuel energy. So this is the data. The demand has been so high that renewable energy has not been able to really sustain that kind of demand. So this is something which one has to understand. And coming back to the data of India, we are producing CO2 at the rate of 7% per year increase, means rate at which it is increasing. So today we are almost 3 billion tons of CO2 every year, and it is increasing by 7% per year. Now, if you see the target of 500 gigawatt of solar panels by 2030, we are not going to meet it. But let me tell you one more data. So right now we are adding 16 gigawatt of solar panels every year. Let's say we will improve a bit on that. But then the rate at which our energy demand is increasing is more than that 16 gigawatt. So that is also one aspect which we'll have to always remember. The other data which I would like to give you, there are people who are talking about that we will be able to do much better by CO2 capture and sequestration, but the cost is a big factor. Today, the rate at which, I'll tell you the data, in India, if you're using Indian coal, you produce electricity at 3.5 rupees per unit. And if you are using Australian coal or Indonesian coal, you produce electricity by around 4.5 rupees per unit. Now, with this low rate of electricity, today 400 million people in India are not able to afford electricity. So that's the data. If we are going to increase it to even twice as much, which will be a very modest number if you are going to implement some of the CCS technologies, you can imagine how many people in India will be able to afford that electricity. And this is not only a story of India, it will be a story for many other people around the world where they will not be able to afford electricity if we talk about capturing the CO2 and all. Coming to the renewable, what exactly we are doing better is the solar, as I was telling you. Sorry. So if you see here, we have been ramping our solar installations. Very recent data up to 2022 is around 60 gigawatt. We are increasing almost 16 gigawatt every year. So you know, it's roughly 150 gigawatt we have done so far. Not all of that is producing, but we assume that by 2030 the target was 500 gigawatt. We will be able to reach around 300 gigawatt. We will still have a big shortfall in our target by 2030. Installation capacity I am talking about. Now, if you are producing solar, what exactly you are getting? You are getting electricity. Now, you are getting electricity for 6 hours a day at max. That electricity has to be stored, has to be converted into some form so that we can use for the remaining 18 hours when sun does not shine. One of the approach could be that you can do it with batteries. I don't want to talk about batteries in today's talk, but the other option is hydrogen, and this is why I have been talking about hydrogen. So, you convert this electricity into hydrogen, and then you basically do whatever you want to do with hydrogen. It could be a carrier, it could be a feedstock, it could be energy itself. But then let's look into the proponent of renewable energy. Where the renewable energy is coming from? You see here, 55 kilowatt of electricity you will have to consume to produce 1 kilogram of hydrogen. Okay. Now, if you are going to transport and store this hydrogen, that will cost you electricity. But let's say the hydrogen which I have produced, I have put a fuel cell just next to it, and I am producing electricity back from that fuel cell. That is 1 kilogram of hydrogen will only produce 30 kilowatt hour of electricity, that is 30 units. So, you are losing 25 kilowatt over here. And if you are adding the cost of storage and transportation of 1 kg of hydrogen, that consumes 10 to 15 kilowatt of electricity depending upon how far you are transporting, what is the process by which you are transporting, what challenge you have to face here is that. So, ultimately you are getting only 50 kilowatt of electricity out of it. Okay, it means there is a 45 kilowatt of shortfall. How we are going to bridge this 45 kilowatt hour of shortfall? We are doing it by solar, but then this is for 1 kilogram of hydrogen. I don't want to go further because I have limited time. You imagine how much hydrogen will be required. Today the total hydrogen capacity is only 4% of total required energy requirement, only 4%. So, just imagine if you go to 100% of hydrogen economy, even though hydrogen economy we are talking about 1985, we have not been able to reach there. So, we have reached only 4% of hydrogen economy today. So, the amount of solar panel will be required, the land required, and all those things you can do a very nice calculation. It is not something which is rocket science. I am pretty sure everyone around in this particular room should be able to do it. So, the question I am trying to pose here is that getting hydrogen is going to be very expensive. It is not going to be that cheap, and it is also not that good in terms of sustainability. We are actually talking about it, no doubt. Now, when it comes for carbon dioxide capture and sequestration or utilization, you see there are two different sources of where you can basically capture your CO2. Each of these has certain advantages and disadvantages. The advantage over here is that the gas mixture which you are basically going to capture CO2 from is going to be relatively free of SOx and NOx. So, your active material which you are going to use for capturing the CO2 is not going to get deactivated that fast. The challenge here is that the active material which you basically use for capturing the CO2 also have some SOx and NOx which comes from the industry that gets deactivated a little fast. But the bigger challenge is something which I am going to talk about in the next slide. But once you have captured the CO2, let me tell you some of the numbers which actually is something which you will have to understand. If I am going to capture CO2 with the best process available today and in future also, I do not think there is a lot can change over here, because thermodynamics you cannot beat. We have increased the entropy, or to reduce the entropy you will have to spend energy into it. So, if you talk about a 500 megawatt of electricity generation by a coal based power plant, minimum 25% of that energy is going to go in just capturing the CO2 which you are emitting. It basically means that around 500 megawatt of electricity comes around 325 megawatt. Once you have captured it, then you will have to transport it and sequester it. That is another 25% penalty which goes there. So, basically the point I am trying to make is that a 500 megawatt of power plant becomes 250 megawatt power plant if you are going to implement capture and sequestration. That is basically means it still look good, that okay, we are able to get an electricity which was at 4.5 rupees per unit. Now, I am able to get it at 9 rupees per unit. Not too bad, because still 2-3 years back, most of us in India were paying 200-300 rupees for one cylinder of LPG. Today, we are paying 1000, 5 times of that. We pay and we are happy about it. So, I do not think that is a big deal, but the challenge is there. We will talk about what is the big deal though. The big deal here is this: the capture cost. People yesterday talked about, Bhima Satri gave a number of $85 per ton of CO2 capture in US, that is their target from point source, and $185 per ton for direct air capture. The Indian data, I will tell you, there is a 20-ton plant in India. There are many such plants actually in India. They say 4 rupees and 65 paise per kilogram of CO2 captured. That comes out to be roughly $50 per ton. So, the data which is coming from international sources and what is Indian data is pretty similar, $50 per ton. Now, when we talk about $50 per ton, the number of CO2, the amount of CO2 which we emit is like 3 billion per ton, 3 billion tons of CO2 per year. We see what is the kind of cost we are talking about, where we are going to, who is going to pay is a big challenge. But more than that, I will tell you. So, when we talk about CO2 capture, if you look into the literature, all scientists like us, chemists and engineers, they will talk about a material which will be able to capture CO2. The material could be zeolite based, could be metal organic frameworks and all. So, I do not want you to read through this particular data. What I am trying to point over here, that if you look into the literature, you will see there is 0.1 gram to 1 gram of CO2 per gram of material you are going to use. Now, if you talk about 3 billion tons of CO2 capture, basically means that you need up to 3 billion tons of this particular material. Now, those who are working with metal organic framework and similar material, you can imagine they will hardly produce you 1 gram or 2 gram in many months. So, this is the kind of requirement we are talking about. So, there is other question. In literature, you will see most of the time people focus on that I have been able to achieve little extra CO2 capture in my material. So, some would say 100, some would say 110, some would say 150, and that becomes our nature paper. The challenge is not that. The challenge is how much we are able to recycle, because this problem is about recycling. It is not about capturing, how much you are able to capture. The challenge is if I have to capture 2.9 billion tons of CO2, then I need at least 2.9 billion tons of this material, which has to be regenerated by almost 100 or 1000 times. Today, you look into the data in the literature, not a single metal organic framework would work for more than 10 times. They are so unstable in presence of moisture, in presence of SOx, NOx and all. GIFs and all have slightly better recyclability. So what I am telling today, I am trying to say here, if you are going to focus on a material, don't try to focus on how much I can capture, because however large you can capture, it will be a tons of material which you would need. Whether I will be able to recycle it 100 times or 1000 times or not, that is something which has to be the focus, not that okay, I am going to capture so much of CO2 in my material. So this is a big challenge. You please understand, 3 billion tons of CO2 in India, we cannot produce 2.9 billion tons of MOF. The problem is this: if I am going to produce 2.9 billion tons kg of MOF, which assume I have been able to produce somehow and recycle it 100-1000 times, a material, I will tell you, steel when it is being produced with modest data tells that 1 kg of steel produces 3 kg of CO2. Okay. Metal organic framework, which is an exotic material or similar material which has multiple steps, at least 3 different steps are there. 1 kg of this material, if you produce, you will produce minimum 10 kg of CO2. Hydrogen, today we produce 1 kg, we produce 20 kg of CO2. This is the data. So the point I am trying to make, if you are going to produce an exotic material like metal organic framework, can you do it with less than 10 kg of CO2? So the minimum required is that 10 times recycling. Otherwise, you will not be able to capture the CO2 which was produced in manufacturing the material itself. So this is something which people still don't focus on. This is proper life cycle analysis and sustainability which you will have to talk about. The second point which you will see, if you are from academics, you are from industry, then you would say that okay, we have figured it out, we know from last 30-40 years oil and gas industries has been doing it. Monoethanol amine or a derivative of monoethanol amine is able to do it. Now let me tell you the sustainability of this particular problem. See, you produce monoethanol amine, you are producing monoethanol amine by these 2 molecules. It's not coming from thin air. If we are talking about producing monoethanol amine, we will have to produce it from some raw material. The raw material for monoethanol amine is this: ammonia and ethylene oxide. Now, when we talk about $50 per ton of CO2 capture, neither we are talking about green ammonia nor we are talking about ethylene oxide which is produced through green ways. Ammonia is still grey ammonia which we use. Ethylene oxide still comes from the same hydrocarbon resources under the earth which we don't want to use anymore. Okay. So the question is that if I have to go in future 20 years, 10 years down the line and expecting that this $50 will come down, where it will come down from? This will increase. More challenges, with more stringent conditions, this cost is going to always increase. Green ammonia will not be produced at the rate at which you are producing the grey ammonia or the black ammonia today. Ethylene oxide will come from where? If you are not using fossil fuel, then it comes from biomass. It comes from the same CO2 which you are emitting, and then you need hydrogen source. If you do not have hydrogen, how you will produce ethylene oxide? So the question here is that, and you saw how efficient the hydrogen production scheme is. Yeah, 5 minutes. Okay. So the question I was trying to say that we have to talk about all this with this information in our background, understanding that okay, these are a challenge. These things is challenging, and we will have to understand it. So one thing which I was trying to tell, and typically I say that when you are trying to identify a material to do some of these things, try to look for a material which is not very exotic, simple, which can be recycled multiple times, and this is going to make it much more sustainable. So we have a few other processes in our lab. I will show you few data. This is the largest direct air capture unit right now, just recently been started in Iceland. Orca it is called. You know how much CO2 it captures in a year? 4,000 tons of CO2. What is the scale? It's 1 second worth of CO2. 1 second worth of CO2. How many of these you will implement? This is the question which we'll have to ask actually. We say all this, that we have captured CO2 and we have used water and we split it and convert it into aviation fuel. The sustainability, look at that. Okay, this is something which is important. This is a plant which is in China, which converts 160,000 tons of CO2 into fuel every year. Look at the structure. This is not even 10% of the total structure. Remaining 90% of the structure is somewhere else, which is not visible over here. You see the footprint, carbon footprint of this particular process. Now, this particular process is converting 2 minutes worth of CO2. This is the largest plant, 160,000 tons of. So these are the reality. We will have to always understand the reality. So this is what I was trying to say. Obviously, since I am running out of time, we have a process which just uses water, but then this process also have a challenge that it cannot work with 15% or 10% CO2. If you have 25 or 30% CO2 in your feed, this is excellent process. It's not a chemical reaction, so the regeneration is not a problem at all, because if there is no chemical binding, then regeneration is not a challenge. If it's only physical interaction, you can always get back the entire material. So we will I will skip to what we are basically doing here. If you look into this, that we have a gas mixture, we have a gas mixture going in from here, and there is just water over here. CO2 goes and form hydrates, and what you get out is relatively pure nitrogen. Obviously not 100% nitrogen, since we are not talking about a chemical process. This is how hydrates look like. This hydrate, solid hydrate, has just CO2 in there, and it will automatically dissociate, and you will be able to get back your CO2. So ultimately we have demonstrated it and all. We have done multiple. So other than this, we also have other processes. Some of you would have seen this particular setup which we have recently got, but we have done a lot of work on fundamentals of how to design some of these molecules which can basically capture the CO2 and recyclability and all those things. We have another direct air capture setup available. Some of you, if you have time, you can come and visit this. So if you look into this, we have basically detections inside this particular room to basically capture the CO2 from this room and look into. So there are all kind of analysis by measurement and all. So ultimately you have captured the CO2. Can I get 2 more minutes? The question is that what you are going to do with that captured CO2. Obviously, when you are going to utilize that CO2, you need hydrogen, and we have seen what is the story of hydrogen so far. It certainly is very bleak at this moment, but capture and utilization will give you a product which is going to be very costly, because if you are going to have 15 rupees per kilogram CO2 available, and if you are going to add 250 rupees per kilogram hydrogen with it into it, the product which you are going to get will be like 300, 400, 500, depending upon how much is the process cost. So now at the cost, when we have 3.5 rupees per kilogram coal available, and we are not able to support 400 million people who are living without electricity. So when your raw material becomes 500 rupees per kg, you can imagine the cost of the product. So where you are going to sell that particular product? That is something which is very important. So the question is that if I am going to capture $185 per ton of carbon dioxide, if I utilize it, the product is going to be double of that cost. It's better to rather just sequester it, because then it's not going to be a problem, because you are anyway going to have so much of CO2 that you can't have a market for that. So the only thing is that you'll have to sequester it. So for sequestration, we also have a demonstration unit. What we do, I will just show you the last data sheet over here, is that you basically capture the CO2 and put it under the seabed 100 meters to 1000 meters below the seabed. This is not an aquifer. This is any unconsolidated sediments which has pores, which has water. You expose CO2 into it. The temperature and pressure conditions under the seabed are such that this will automatically convert into solid hydrates, and it will remain there forever, because these are solid. We have sequestered the CO2. So this could be one approach which we have already demonstrated, and that's all. So I hope I have given a slightly realistic picture of the CO2 capture, utilization and sequestration aspect, and how quickly we would be able to decarbonize our economy. Sorry, I was running like an express train, but I hope I have conveyed the message.
So thanks so much, Rajnish. I always admire someone for talking the reality, and definitely Rajnish is one among them. Like, who talks, this is the reality, accept it. And now I think we'll open the floor for questions. Yeah, we have one here.
I have a Bhima. Can you hear me? I have a question for Professor Raj, a comment more than a question. Oh, okay. Hi, Professor Rajnish. This is Bhima Sastry from the US DOE.
Hi.
We've met a few times.
Yes.
Excellent presentation. Just have one comment more than anything else. You mentioned direct air capture and how expensive it is and how many you may need even to get to any target level. I think the idea of the direct air capture, and this is the comment I just want to make, is that most electricity produced that is needed across the world is base load, which means, like nuclear or coal plants are always operating at some base load. And now with the advent of renewable energy, if they come in, those baseload reactors are unable to cycle and move up and down quickly. So when you have excess electricity, it makes sense to use the direct air capture in those type of locations. And that's the only place, I believe, where it makes commercial sense to have, is to take that offset baseload electricity, because there's renewable electricity coming in, and use that excess electricity to run your direct air capture and kind of make some impact on the environment. That's the way we are looking at it at the Department of Energy, and I just wanted to share that comment. But an excellent presentation, kind of covered everything that is so important to CCUS, and thank you for that.
Thank you, Bhima. So I just want to have give a comment on this. See, direct air capture is certainly very important and will become has a very big role to play. Since today we are not able to capture CO2 from point source, very soon we are going to talk about CO2 concentration in atmosphere, which is around 550 ppm. Now we are talking about 550 or 600 ppm. How you are going to get that CO2 down? The only option for you is to do it through direct air capture, and Bhima Sastry is right over there, that at some point of time we are going to have free electricity for 6 hours a day, but then this free electricity which is available for 6 hours a day has many takers. For example, if I am going to talk about CO2 capture process, none of the CO2 capture process will work without of this free electricity which is available for this 6 hours a day. So everyone is eyeing for that 6 hours of electricity which will be available free. I don't know who all will be able to use that. So that's another point which I wanted to make.
Thank you very much for the presentation. I think I was put all of us on ground level. So 2050 is around the corner, and you show that getting there is going to be very difficult. What do you think is our plan B if we cannot sequester the CO2 and we cannot produce the hydrogen?
There are many plan Bs, but I will not talk about that. It's going to be a science fiction here. So unfortunately, we do not have time, but we will talk about it maybe one-to-one. See, I certainly believe that there has to be plan B, C and D. Obviously, CCUS and hydrogen economy and all will be also part of the same plan, but there will be some exotic plans which also will ultimately come into picture. Nuclear is obviously a good plan B, I would say. We have not really tapped all the potential of nuclear yet. Given we have been able to manage the after effects of nuclear, we know better now how to handle all those things. I think nuclear is going to play a significant role. But there are many science fiction based processes which we will, I love to discuss all Star Trek and Star Wars over here.
Yeah. Thank you for the energetic talk. So my question is related to, let's take the example of if we are burning 1 gram of petrol, and that 1 gram petrol converting some CO2 and energy, and the method or the methodology you discussed now to capture those CO2 and put back under the sea. So how it is energy efficient? So like how much energy we are generating from the petrol, and finally if we are dumping those CO2, then how much energy required? So how much energy, so how the whole process is energetically efficient?
No, not efficient. I agree with you. It's not efficient at all. See, the challenge is very simple. So far what we have been doing, we are digging carbon from under the earth. We are utilizing the energy and releasing the CO2 back to the atmosphere. So this is only half of the cycle. Now, how long you can sustain by doing half of the cycle, unless and until you close the cycle by capturing that CO2 and put it under the earth? Otherwise, there is no solution, no? So whether it is energy efficient or not energy efficient, but sustainable it will only be when you are going to capture that CO2 which you have released to the atmosphere and put it back under the earth. Because if you cannot do it, then it is not sustainable. You will have to face a challenge in today, tomorrow, or 100 years, 1000 years, 5000 years down the line. So this is the challenge, that if we have to be sustainable, we will have to put all what we are producing as human activities, put it back where it came from. So this is what we are trying to do.
Basically, if you can use the renewable energy like direct solar or wind to dump this CO2.
That is what we are saying, that see, today we are talking about we will not use fossil fuel, but then fossil fuel is a good source of carbon and hydrogen. More than carbon, it's a source of hydrogen. See, unlike hydrocarbons which comes for free, we do not have hydrogen. White hydrogen is very limited. So we do not have hydrogen, we have to produce hydrogen. The challenge comes from because of all the processes which is required to produce hydrogen. So if we had huge amount of white hydrogen, we would not be talking about all this. We could just tap all those white hydrogen and do whatever you want. But the question again, as I was asking yesterday, are we ready to junk the entire carbon, which is a source of such a huge energy? That is something which we'll have to ask actually. Is it possible for us to junk the entire carbon and we only rely on hydrogen? At least today I don't see that we can do it just by hydrogen. We will have to keep that carbon in the mix of energy for really long time, because the amount of the density of energy which you get from the carbon is not available in any other source as of today.